All right. Okay, we'll just wrap up what we were talking about yesterday. I'll get a chance to maybe work on some of your stuff in class, homework in class, get that out of the way. So we had talked yesterday, remember, about real numbers. We had talked about, let's see, if I just backtrack a tiny bit here. What's going on? Oh, my goodness, I'm kidding me. There we go. That's better. Okay, we had talked about sets of numbers, right? We talked about natural numbers, whole numbers, integers, rational numbers, and irrational numbers. What did we say about the set of, just remind us real quick, what's kind of our working definition of a rational number? What's it mean to be a rational number? And what does the word ratio mean? It kind of gives us a little hint. I don't know if I mentioned this yesterday or not, but when we're talking about rational numbers, it gives you a big hint right in the name of the word. Ratio is just a fancy name for what? Fraction, yeah. So what's our working definition of a rational number then? One that can be written as a fraction. Good. Okay, and we kind of talked about some math, some ways that we can symbolically write math. We're going to start, just sneaking into that a little bit, a little more than you used to. As a decimal, what about rational numbers can be written as what? If you're going to take a rational number, one that can be written as a fraction, and write it as a decimal, what are only two things that could happen? Repeating and terminating, good. And then we said at the end that irrational numbers are just the real numbers that are not rational numbers, right? So then, logically, they're the ones that can't be written as fractions. It's going to be the opposite of what a rational number is. And so they're the ones that can't be written as fractions, and as decimals, they don't terminate, and they don't repeat. Let's practice this just a little bit. I don't want to spend a lot of time on this. I mainly just want to get at how would you do this problem. So if we're going to write, these are all rational numbers, agreed? How do we know? Fractions, there you go, they're fractions. So we want to know in each case, is it going to be a terminating or repeating decimal? Let's write them as fractions. Okay, how would you do that? Okay, and would you do it in your head or on paper, or I know what I would probably do. Calculator, yeah, we're just going to plug it in a calculator. You could divide it out using long division or something like that, but we're not going to. And you just see what you get, right? And so, for example, the second one, well, that one we could have done in our head. 15 divided by 5 is just plain old 3, isn't it? That's an integer. Is an integer a rational number? It is, isn't it? If we go back to this previous page, we said that this was the smallest set of real numbers. This is a slightly bigger one. Notice that the set of whole numbers includes the set of natural numbers plus just that one extra number, the 0, right? Integers includes whole numbers, but we also add the negatives. And then rational numbers, any number that can be written as a fraction is a rational number. Well, what about like -2? Can you write that as a fraction? You usually don't, but could you? What would it be? Yeah, you could just divide by 1 always, couldn't you? So really all the integers are rational numbers. We just don't write them that way because it's inconvenient. Okay, so this one clearly is a rational number, but it works out to just be a nice convenient integer. The bottom one, if I divide 13 by 25, on my calculator, I get 0.52 stop. It terminates, right? The top one, though, the top one's a little bit trickier. On the top one, -5/7, if I were to punch that into my calculator, it's going to keep going and going and going. How do I know where to put the bar over that? It is repeating. It's a rational number, so we know it's got to either repeat or terminate. But how do you know where to put the bar? Why couldn't I stop with the bar like after 714? because it doesn't repeat that, right? We have to put the bar over the part that is being repeated over and over again. So if I were to let this number go as a decimal, get really big as a decimal, it's just going to be negative 0.714285, 714285714, etc. Right? It just keeps on going. And so the part that's repeating is the part that gets the bar. Okay, what about these? Determine whether each of the following numbers is rational or irrational. If it's rational, determine whether it's a terminating or repeating decimal. So what do you think? First one. Rational or irrational? Rational. Yeah, it kind of tries to trick you because it looks like a square root. And as we said before, square roots, if they don't work out well, they're irrational. But this one does. 25 is a perfect square. Square root of 25 is just plain old 5, so that's rational. Second one. Say it again. Rational or irrational?
Irrational.
Irrational? Why do you say irrational? Okay, you're right. You're right. So it may be a really ugly decimal. Now think about this question again. Rational versus irrational. What's our definition of a rational number again? Maybe written as a... Oh, okay, well, it's a fraction, right? So it has to be rational. It may be ugly as a decimal, but it has to be rational. Okay, so that one we can put in the rational category. What about C? Let's take a vote. How many people say rational? How many say irrational? Oh, we're getting lots of hands. Okay, good, good. So, what's our thinking on this one? How'd you come up with? Somebody help me out here. What do you think?
It's not a perfect square.
It's not a perfect square. Good. The number inside the radical is not a perfect square. Think what perfect squares are. Numbers that are squared, right? So 2 squared is 4, so 4 is a perfect square. 3 squared is 9, so that's a perfect square. Well, we missed 9. We're too big for a square root of 9. But the next one we hit is what after 9? 16. So 11's between 9 and 16. You know, guaranteed, this is irrational. It's going to never repeat, never terminate as a decimal. D? Rational. Okay, what about E? Look closely at E. It's trying to be pretty tricky, isn't it? It sure wants to be irrational, but what's wrong with it? It looks like it's repeating. There's a pattern, but is it a repeating pattern?
No.
Yeah, you see it's, now let's kind of look at this here. The part that seems like it's repeating, like we get this, I guess 303 maybe, but here it's 3033, and then 3033. You see what I'm saying? It grows every time. You get an extra 3 with each batch. And so you can see that it's a recognizable pattern, but it's not a repeating pattern. So what does it have to be? And the ... tells us it goes forever. Doesn't repeat, doesn't terminate. It's got to be irrational, doesn't it? Right? Okay. Okay, next step. So now let's look at, this is something we do a lot in math. It's called a Venn diagram or a set diagram. Not that that's really important, but what we want to do is we want to represent the relationships between all of these subsets of real numbers. So the whole page represents the set of real numbers, but we're going to try to divvy this up into sets and subsets. So our goal is we want to put all of these subsets into the right places in this set diagram. Okay? Natural numbers, N, W, we're going to use to represent whole numbers, I for integers. A lot of times integers is actually a Z. But for this example, it's an I. Q is rational numbers, and then Q, that's called a prime. Q prime would be irrationals. Now, how am I going to do this? Let's think logically. Let's start with maybe natural numbers. Somebody help me out here. Raise your hand, somebody, and help me out. Where am I going to put that set of natural numbers? What do you think? Yes, sir.
Right in the center circle.
Okay, the center one. Good. What's your thinking? How come this one and not this one?
Because it's just the whole number. It doesn't go down into a fraction or a decimal.
Okay, but so you got to start it. Whole numbers, maybe not a great word to use though, because that's a different set. What do you think?
I was going to say they're the smallest subset.
The smallest subset, right? That's the smallest subset. So that's the one that has to be contained by all the bigger ones, right? So that makes sense. We're going to go, set of natural numbers goes there. Okay, what do you think? Someplace, what can we do next here? Whole numbers. do you think? Where are the whole numbers need to go? Where are the whole numbers? Why don't you say that again? Second smallest circle, good, because that's the next biggest subset. So the natural numbers just contain 1, 2, 3 on up. The whole numbers add, they include all that stuff, but they also add the 0. That's it. That's the only extra element that's not in the natural numbers, but it is included in the whole numbers. Okay, what's after that? What's going to go there? Integers. Good, because now we're going to add some extra stuff. Now we add all the negative natural numbers, right? What's next? Rationals, good. So rationals get all of that stuff. What else is not included so far in any of those other sets that's going to show up in this bigger bubble? Okay, fractions. Fractions that don't reduce to integers, right? So stuff like that, m over n, where n is not equal to 0. Okay? And then here's the tricky part, though. And this is kind of an important point. What about the irrationals? Where are they going to go? They've got to go outside, because really this is the part that I kind of tried to get at yesterday, but it helps to see it graphically like this. The irrationals is everything except those, right? All of the real numbers that are not rational. So they're a separate set. They don't overlap at all, do they? Right? So we might do something like this. We might say the irrationals go out there, right? Everything that's not included in that big bubble would then fall into the category of irrational numbers. There's different ways to represent that. Here's a different take at it, very similar. I just pulled this off the internet, and this is not, you can find a ton of stuff like this. If this whole thing is the set of real numbers, here's just a different way to represent that. Everything in the green would be the rational numbers and its subsets, and then separate from that are the red numbers that are the irrational numbers. Okay. Same idea, same concept, just slightly different representation. And then I'll attach maybe just another couple here that I wanted you to get an idea where we're going with this. We'll pull this one up again in about a month and a half, or something like that. Okay. Notice what's different here. We've got the set of real numbers that's included everything, all the real numbers are in that blue bubble. Rational numbers and their subsets, and the irrational numbers that are separate, right? But what else has been added here? Yeah, okay, we notice now, and you just kind of see the relationship. You can forget about this for a while. But as I mentioned yesterday, the real numbers are actually not the complete set of numbers. It's all you've ever used. Everything you've ever done has been contained in that light blue bubble up there somewhere, right? But there is a larger set of numbers called complex numbers, and the real numbers are just a subset of that. We'll get to that later. Okay. All right, so this one I just threw up there. I mean, don't panic. That's nothing we're going to do this year. But I just wanted to make a point that numbers seem pretty straightforward. You've always used numbers and just taken them for granted. No big deal, right? But actually there's a lot of relationships going on there that you may not have known about. You know, we've got all our sets and subsets that we talked about over the last couple days. But then in addition to that, in addition even to the complex, we can kind of slice and dice these numbers in some ways that you may never have even thought about. Like you could talk about, for example, transcendental numbers. These are numbers that are another type, another category of number that we won't probably talk a lot about until a little bit in pre-calculus, but mostly in calculus. The algebraic numbers. Algebraic numbers overlap with both the complex and the reals, but there are some real numbers that aren't algebraic, and there are some complex numbers that aren't algebraic. And so there's all these other definitions that... Hang on one sec. Hey, Dan, what's up? Oh, perfect. Can I give you a call? I'm in class right now. Can I give you a call second period? Awesome. Thank you. Bye. Okay, so you can see that this can get pretty complicated, right? It gets pretty involved. Later on, as you study math, this will make more sense. Don't panic now, though. I know that looks like your heads aren't going to explode. I promise. Okay, so quick summary. You know what? Let's get this. We'll just jump right into this. Why don't you pull out your green sheets, and let's just kind of go through this one real quickly together, and then you can jump onto the purple sheet, which is that's the homework. And when you're done with that, you're done for now. Let's assign some letters and give you a second to kind of work through this, and then you can give me some answers. Give you five minutes or so to work on this sheet. Let's get some symbols. What's our symbol for the natural numbers? N, capital N. Whole numbers? W. Integers? I we did before, but really most of the time it's going to be a Z. Let's go ahead and make it a Z. Rational numbers? No. Okay, now R, why wouldn't it be R? You think it ought to be R, but what probably gets the R? Real numbers. These are all parts of the set of real numbers, and real numbers get capital R. So rational numbers got Q, there you go. And then irrational numbers, we call Q prime. Yeah. Okay, and let's throw some quick examples up. How about integers? What are integers? What are some examples of those? Say it again. -1, 0, 1, etc. Right? Rational numbers. Give me an example of a rational number that's only rational but it's not 1/2. Good. As a decimal, what might that look like? Say it again. I got too many answers at once. Okay, 0.5. There you go. Okay. Give me another decimal. Something that's maybe a little different than that one. Okay, good. So we could do something like, we could do that. Let's think of a different one. How about 183? What's the number being repeated there? Just a 3. Good. Whole numbers. Give me some examples of whole numbers to sort of illustrate. 0. Okay, then we could just do that if we wanted to. That's the whole set, isn't it? Then natural numbers, we know that one, right? Counting numbers, 1, 2, 3. Irrational numbers, a couple examples. Pi. Square root of 3, good. I got one for you. Have you ever heard of that one before? The natural number E. We'll talk about, in the very end of the year, we'll talk about that one. Different E, but right idea. Different E. Okay, so why don't you quickly wrap this up? So there's the first page, and then try this also. For each of those, see if you can name all the sets that each one belongs to. Let's just take one as an example. What if we did this guy right here? What are all? We'll just use the symbols. Probably let's start with the biggest set, and then all the subsets would just naturally get included. So Q, okay, and if it's in Q, what else comes with that? Everything, everything except Q prime. So we get Z would be the next one down, the integers, and then W, and then what's the last one? N. Okay. So why don't you guys take 5-10 minutes and just work through that and go from there. Okay, so that's the whole first page, isn't it? Yeah, good. Come back together here. I want to look at one more quick thing today, and this will be, I think, a little quicker review. So I want to look at, frozen. I want to look at some properties of numbers and equality here. So okay, do you remember these properties? Like commutative, associative, remember talking about those in Algebra 1? It's been a while. Okay, so the commutative property is the one, let's just talk about these. I'm going to give you some ways to maybe think about that you could help you remember what they are. Because they come up a little bit. The commutative property of addition or multiplication, we'll talk about both of those, states that numbers can be, the order can be changed. It doesn't change the result. So for example, for addition, we'd say that if we're adding two numbers up, A plus B, we can exchange their positions, B plus A, and it doesn't affect it, right? Here's the way I suggest is a good way to remember that. When you commute to work from home, what are you doing? driving there probably, right? You're changing your position. You're going, your position's at home, and your position's gonna end up at work, right? That's when you commute to work, and then at the end of the day, you commute back home. That's, everyone goes, that's called the commute. That's what's going on here. Numbers can also commute. They can commute from point A to point B. They can switch their positions, and it doesn't impact, like if this was a 1 and that was a 2, 1 plus 2 obviously is the same thing as 2 plus 1. Works for multiplication as well, right? Here's another example. -2 plus 7 is the same as 7 plus -2. It works for multiplication. A times B is the same as B times A, right? There's an example. -11 times -4 gives us the very same thing as -4 times -11. Got a question for you. What about subtraction? Think about that one for a second. It doesn't work, does it? Doesn't work for subtraction. Right, if we do something like 17 minus 5, that's not the same thing as 5 minus 17. What about division? No, it doesn't work for division. 20 divided by 5 is not the same as 5 divided by 20. So this is not unique to the commutative property. All these properties we're talking about only work for addition and multiplication, but they don't work for subtraction and division. Okay, so there's commutative property. What about the, oh, that's big. What about the associative property? Remember what that one tells us? Remember that? I wouldn't, probably. I've used this forever. What's it mean to associate with somebody? Group together, right? You talk about like the law associates in a law firm, if they're associates, they're grouped together into one company, right? So this is about grouping. The associative property says, like for addition, it just says that, I guess we're doing multiplication first. Okay, that's fine. It just says that if I'm multiplying, for example, 3 things together, I can group those in any way I want to. I can only add or multiply things together in pairs, right? I mean, it doesn't make sense for us. Here's an example. Like if I were to try to multiply together the numbers, let's say 2 times 3 times 4. What's the answer? 24. Okay. How'd you get that? It's almost a dumb question. It's so simple. But what'd you do to get 24? Say it again.
I did it weird. I did 3 times 4 times 2.
That's fine. So you could do 3 times 4 is 12 times 2, right? That's fine. What's another way? Okay, 2 times 3, 6 times 4, same answer. 2 important points here, though. Notice that when you multiply stuff, and this is true. I mean, this is always going to be true. When you multiply things, you always have to multiply in pairs. You have to do it one step at a time, don't you? Right? It doesn't really matter which ones you multiply first, though, according to the associative property. You can group this any way you want to, but you still have to group it to multiply. Okay? What about addition? Is that going to work? If you're going to add all those up, you could add the 2 and the 3 first. 5 plus 4 is 9. That's fine. You could add the 3 and the 4 first. 7 plus 2. Get the same result, right? You can group them any way you want to. That's what the associative property tells us. Okay, and there's some examples. Works for addition also, right? And another probably stupid thing, I mean, I'm not trying to insult you here, insult your intelligence, but it's a point that I just want to make sure everybody's clear with. Why do we use like A's and B's and C's instead of just sticking with numbers when we're talking about these properties? Like when you look at any textbook and they ask you for the associative property of addition, it's going to look just like that right there every time. What's the point of this? And it probably just seems obvious, but why? Why do we use A's and B's and C's? Because it represents any possible number, doesn't it? Right? You see the power of that. We don't want to just use this one example because then we're stuck with that one example. A and B and C, they could be any numbers, right? Any real numbers, okay? Is this going to work with subtraction and division? Try it. Does it work? How about this? 8 and 3 and 15. Is 8 minus 3, the quantity 3 minus 15, the same as doing the 8 minus 3 first and then subtracting the 15? No, doesn't work. It doesn't work for division either. Okay. Once again, only addition and subtraction. Okay, how about distributive property? That's one you use more often. You don't often call it anything, but what's it mean to distribute? What are we doing when we distribute? That, right? You're probably used to seeing this on your paper, or maybe teachers have done this in the past. Does that look familiar?
Yeah.
Okay. So when we distribute, that's kind of a combination of both multiplication and addition, isn't it? But there's a common mistake that people can make with this. So combines both of them, but we say that it's multiplication over addition. The multiplication has to be outside. Sometimes what people want to do with this, and there's a good example somewhere on here, is something like this, right here. Okay, does that work? 6 plus 3 times 5, is that the same thing as 6 plus 3 times 6 plus 5? Think about that. 3 times 5 is 15, 6 times 15, or 6 plus 15, sorry, is 21. I'm going to get something way different over here, though. If I tried to distribute this, it doesn't work, right? You can't distribute addition over multiplication. It has to be you're multiplying a quantity. When I say quantity, does that make sense? What do I mean when I say quantity? What are you always thinking? When I say 6 or A times the quantity B plus C, what's that telling you about the B plus C? They're in parentheses, yeah. Whenever in math we say the quantity, it means it's grouped together in parentheses. So I have to multiply by a quantity where there's some stuff being added. I can't do the opposite. It doesn't make sense to do it this way. And you probably, I'm sure you know that, but just that's a common mistake that I see quite a bit. Okay, how about, what about something like this? I want to look at this example. This in particular. I mean, there's a ton of them I could have used, but this is pretty good. If I want to do something like 12 minus 5 plus 3, I want to simplify that into one number. We're going to use the word simplify a lot here pretty soon. What's one strategy I could take? Okay, so one thing I could do, and this is kind of a topic for early next week, we're going to talk about simplifying using order of operations. PEMDAS, right? So we could use PEMDAS, and we'll come back to that. PEMDAS is huge. It helps you so much, all the way through calculus. You can use PEMDAS, way more than you think you can right now, I promise. So if you follow order of operations, and I'll just write it up here. Now I'm going to write it a little differently maybe than you've seen it in the past. I don't like to just write out PEMDAS. A lot of times, have you seen this before? Oops, sorry. Have you seen this before? I can't even write it. Oh. Okay. There's something wrong with that, and we'll get back to this, but we'll just touch on it today a little bit. What's kind of wrong with the way this is written compared to, I'd say this is a better way. The one in green is I think, far better. Okay, good, because now, first of all, what do these symbols stand for? What's the P? Parentheses, so we're going to work our way down, right, from the top when we're simplifying. So first we'd focus on anything inside parentheses, right, take care of that. What's next? Exponents, none of that here, right? What's next? Multiplication and division, and then add and subtract. But when you write it this way, which sometimes people do, it seems to imply that multiplication comes before division and that addition comes before subtraction. True or false? False. It really should be this way. So when you get to this step, the M and the D, the multiplication or division, you just start from the left and work your way to the right, and whatever you see first, you take care of, multiplication or division. Same thing here. Addition and subtraction are on equal footing. These are pretty simple. We don't even probably need all this stuff, but we'll get back to that. So if we follow PEMDAS, there's in parentheses, that's the first thing we would do. We'd get 12 minus, and then the parentheses becomes an 8. And then we can skip all the way down to addition and subtraction, and 12 minus 8 is 4, okay? Okay, how about if we use distribution instead? Because that's the other thing we could do. What about that? Okay, yeah, let's talk about that. Exactly. Distribute the negative, and that's correct. But really, there's another way you can sort of represent this. And I don't want to confuse you, but I want you just to see the connection here. This is the very same thing as saying 12 plus what number times x plus 3. When I'm subtracting, what am I really doing? I'm adding, like if I, negative 1 in this case, right? Like if I were to say something, different problem, like if I said 7 minus 5, that's the same thing as 7 plus what? Negative 5. Okay, that might seem like a really minor thing, and it is, but it's an important concept that later on in algebra we'll come back to. When you subtract something, you're always just adding a negative. Same thing exactly, right? So right here, 12 minus the quantity x plus 3 would be the same thing as saying 12 plus negative 1 times x plus 3. And so what number are we going to be distributing to the negative 1? Right? That's really all we're doing is distributing that negative 1. And so we get 12 plus negative 1 times x is negative x. Negative 1 times 3 is negative 3. And that's one way to get to the answer. I combine like terms now, don't I? Right? So I get negative x and then 12 plus negative 3, 9. Same thing as 9 minus x, right? You had a better way to do this. It's kind of a shortcut, and I would stick with it, but I just want you to see why it works. If we distribute the negative, here's how we'll probably write it from now on in class. If I distribute the negative, what's that do? If I distribute the negative to the first term, I get negative x. Distribute the negative to the second term, quicker, right? Same idea though. 12 minus 3 is 9 minus x, right? Okay? Identity properties. Okay, this is getting maybe a little weirder. Not something you're as used to. You've talked about them before. They come up, I'd like to give you a little roadmap here. I know we're about out of time. But this is, like, we're going to talk about just addition and subtraction with real numbers. But later on in the class, have you guys ever heard of a matrix before? Not like the matrix, but a matrix where it looks like kind of like a chart on a paper. You seen those at all? Okay, they're different things. They're bigger than just numbers. They contain more information. We'll deal with those later in the year. But these properties, like the identity property, and we'll talk about the inverse property in a second, they work for things like matrices too. So sometimes when we use these really simple models in math, I know they're painfully simple sometimes, but they can be extended to other things too, bigger and more complex than just numbers. Okay? So the identity property. If you talk about somebody's identity, what is that? Someone steals your identity, what are they stealing? Information that is specific to you, right?
That's basically like
Private, okay? It's what, like your identity, if you think about it on maybe just a more personal level, your identity is sort of who you are, right? Okay? So the identity property of addition, these identity properties, they're simply telling us for addition, what's the one number that you could add to anything and preserve its identity, meaning leave the identity unchanged. 0. Yeah, you add 0 to something and it stays the same. The identity is unchanged. What's the multiplication number? 1. Okay? Then yeah, that's simple. Okay, that's important. You're preserving the identity. The value of the number stays the same. What goes with that is the last thing we'll cover today are the inverse properties. It's easier to think about them together. Okay, so the inverse property for addition, here's what it is. I'm going to tell you how you can remember this. The inverse property of addition says that if I add the opposite of a number, I get 0. Okay, here's how you can reconcile this though. What's the identity number for addition again? 0. So we're really just filling in the blank. When we're asking for the inverse, it's like answering this question. I want to know what's behind the blue box there. We're asking the question, what would I have to add to a number to get back its identity? Its opposite, right? So you're always going to add the opposite to get 0. That's what we call the inverse, though. Inverse for addition is opposite. So what's the inverse? Sometimes we call it the additive inverse. What's the additive inverse of pi? Negative 5. What's the additive inverse of negative 11?
11.
Positive 11. Okay. What about for multiplication? We're going to do the same thing. So for multiplication, we're going to say a times what is going to give us back the identity number for multiplication. What's the identity number for multiplication? 1. So this one's a little bit tougher. If we want to get 1 back, what do I have to multiply something by to get that? I'll give you a little hint. A is the same as a over 1. Think about it in terms of just numbers for a second. What would I multiply 1/2 by to equal 1? 2, or 2 over 1. What would I multiply 3/4 by to get 1? 4 over 3. That's just going to be the reciprocal, isn't it? Right? Okay? So we multiply by the reciprocal. And a quick example would be something like this. Negative 2/3, I would multiply by, I just flip the fractions, all I do, negative 3/2. Why does that work? Because when I multiply straight across, look what happens. I can cross cancel, right? The negative times negative is positive. Okay, make sense? All right, let's call it a day. You can keep working on that blue sheet. I won't collect that until Monday. Purple sheet, I mean, exactly.
Same thing, right?